The objective of this video is to derive equivalent X and Y suspension current components for a bearingless motor. In previous videos, we've worked up to a force expression for the forces that appear on our shaft as being a force vector equal to a complex quantity Kf times our suspension current space vector. And in this video, we're going to show how we can write this in terms of our force current gain times an equivalent X current component plus an equivalent Y current component. And the reason that we want to do this is that this is much more conducive for control of the bearingless motor. It helps us to write out our control laws and design controllers if we can consider an equivalent X and Y current component that are strictly responsible for producing X direction and Y direction forces. I want to first review how torque works in a motor and how we use that to create D and Q axis current components. And to do this, we're going to go back to this diagram that I've pasted here on the right side of the screen, which is simply from our notes on torque creation in a motor. And so you can see I've drawn a machine cross-section of a two-pole equivalent motor. We have our X unit vector here on the horizontal line. We've got our two-pole rotor, and we've got angle theta pointing to the rotor's direct axis, which is just its north pole. And then we've got our equivalent winding out here with an axis of alpha t. And as we've been talking about in previous videos, this alpha t is also the angle of our current space vector. So this blue line here, we can simply indicate that this is also the location of a current space vector. It has angle alpha t. And so when we talk about motors having a direct axis, we can also say that they have a quadrature axis. And so this means something both physically for the motor as well as for our current space vector. So the direct axis is always the location of the north pole, and the q axis or the quadrature axis is the location in between the poles. And we can use this to determine our direct and quadrature current as being the projection of our current space vector along those axes. And so our direct axis current is our current space vector projected across projected onto our D axis. So that is at this angle of phi I. And we can do the same thing for our Q axis current. And as we talked about in our previous video, our Q axis current is used to create torque. And we can see that directly from our torque results right here. Q axis current is our current space vector magnitude times the sine of phi I, which we have right here. So to rewrite all this out, we can observe that when we know our direct and quadrature axis current, we can construct our torque current space vector, where again, theta is the angle of the direct axis relative to our horizontal axis, x. And we can also write this in terms of our three-phase motor currents. And if we're being ultra precise about this, we'll put a coefficient c in front of this. If c takes on different values, this space vector transformation is called different things. There's a value of c that makes it a power invariant transformation. You can pick c equals 1 like we've done in our previous notes. You can pick, the point is here to make you aware that you can pick different values of c in order to make these quantities have different physical significance. And that's beyond the scope of today's video. So this is great. We can go from having three-phase currents to constructing our current space vector, and we can go from having our equivalent D and Q axis currents to constructing our current space vector. However, what this doesn't tell us how to do is to go from our current space vector back to three-phase currents. And we can see that that's true because the current space vector actually only consists of two components, a real and imaginary component, whereas our three-phase currents, of course, have three values. So this is an underdetermined system. And if you recall, the way that we resolve this issue is that we talk about a zero sequence component. So our zero sequence or common mode current is the average of our three-phase currents at any instant of time. And in balanced three-phase systems, this is simply equal to 0. In fact, we would like to have this always be equal to 0 because a zero sequence current is a current component that appears simultaneously in all three phases and does not produce any torque and does not produce any force. So we like to say that this is always 0. But now, when we've written these two equations, suddenly we have 3 variables on the left side and 3 variables on the right side. On the right side, we've got I, U, I, V, and IW, and on the left side, we have the real and imaginary components of our current space vector, as well as our zero sequence component, and suddenly we can invert this transformation. We can go from a current space vector plus a zero sequence component and construct our 3-phase currents. And this is the famous DQ transformation, or Park and Clark transformation. So we can write this in vector and matrix form like this. And we can also invert this relationship, where again our direct axis current is related to field weakening, our quadrature axis current is related to torque, and then our zero sequence component is typically just equal to 0. And so I wrote this out as a vector multiplied by a matrix. So CR is a 3x3 matrix. And I express CR as a function of theta because it depends on the rotor's position. We've got this e to the j theta here. And so similarly, CR inverse is going to be a 3x3 matrix that also depends on theta. And this transformation is not particular to currents. You can transform voltages, you can transform flux linkages, you can transform any 3-phase quantity to the DQ0 domain or back from the DQ0 domain. And so in motor control, this is especially useful for transforming currents that you measure with sensors to being DQ currents, and then for transforming DQ voltages that your controllers create to being 3-phase voltages that you apply to your motor terminals with power electronics and pulse width modulation. So here I've written it out in terms of voltages. Okay, so that's a review. This is how DQ current transformations work, or DQ transformations work. Now we're going to do a similar thing, but we're going to do it for X and Y currents. So just like we decomposed our, I labeled this as IS, this should be IT. So just as we decompose our torque current space vector into D and Q axis components, we're going to decompose our suspension current space vector into X and Y components. And we'll start with a P+1 motor. So from our previous video, we had this result, where our force, we cast it into the real imaginary plane as being Fx plus J times Fy, and that was equal to this complex force current gain times our current space vector. And so we can work with this here. And we first notice that if we write out our definition of Kf as being Kf hat times this complex quantity here, we can note that if we define our current space vector to be able to be decomposed in this manner, and we plug that back into this expression up here, we get this result, which is the result that we're after. That is, our x component of our force is strictly equal to Kf hat times Ix, and our y component of our force is strictly equal to Kf hat times Iy. And so we finally get our result down here. Now, I want you to compare this suspension current space vector decomposition to Ix and Iy to our torque current space vector decomposition into Id and Iq. And you see that we basically have the same transformation. Actually, the only difference is that we have this phi-m angle in the suspension current transformation, and again, that was due to our armature reaction field. And so if we assume that our armature reaction field is 0, that is no coupling between the torque and the suspension operation, then we have the exact same transformation. We have this e to the j theta. And so by making this observation, we can write out what our transformation looks like below. And so we get this result. And remember, this matrix is the same as this matrix. It's just that we've shifted it by this angle phi-m. And so in this case up here for torque, we have Iq is equal to our torque divided by Kt. In this case, down here, we have Ix and Iy equal to the Fx and Fy force components divided by Kf. And so you can see here that we're now in a position to regulate our linear motion, that is our x and y movement, in the same way, in the same manner that we regulate our rotary motion. So that is, we're going to take our measured suspension currents, do our dq transformation to get out our Fx and Fy force-producing currents, or x and y force-producing currents. We're then going to feed that into a current regulator in this frame and generate dq or xy voltage references that will transform back to the UVW domain. And so, just as we did this for the P+1 motors, we'll now consider P-1 motors. And we get the following result. So in the case of a P-1 motor, we had the conjugate of our force vector, that is Fx minus jFy. This minus is key, is equal to the kF bar times our current space vector. And so we write this out, and we see that if we define our current space vector in a similar manner, but with a minus sign in front of our Iy term, we can write out this expression down here. And matching the real and imaginary parts, we again see that Ix is responsible for force in the x direction, and Iy is responsible for force in the y direction. And we can carry this negative term through in our current transformation, or in our dq transformations as well. And we'll highlight these negative signs to make it clear in the notes. So that concludes this video. In this video, we have derived the equivalent x and y suspension current components. We've done this by first reviewing how torque is produced from D and Q current components, which we obtain by decomposing our torque current space vector into these D and Q components that rotate with the direct axis of the motor. We then use this analogy to investigate how we can define x and y current components in a P plus or minus 1 bearingless motor. And we'd find that we can use the exact same transformation, but shifted by this angle phi m, which is the angle of our p-pole pair field in the air gap of the machine. We then repeat this derivation for a P-1 machine and find that we get the same result, but with signs inverted on the y components.